and welcome back. Today is our second day talking about parametric equations, curves in the plane defined by parametric equations. I did just post your homework. I realized only this morning that I didn't give you that homework to do over the weekend, which I don't imagine anybody is upset about. And I'm going to do an extra homework set over the weekend. So the homework set that I just posted for you has both 10.1 stuff and 10.2 stuff. 10.1 is just graphing parametric curves. The stuff we talked about last Friday primarily. And the 10.2 stuff is the stuff we're going to talk about today, which is how to do calculus with parametric curves. So I will revisit a little bit of the 10.1 stuff, just a tiny bit to make sure that we're comfy, and then we will start talking about how to do calculus with these things. Let's get in here. This is MAC2312, section 004, which is Calc 2. And today is 11/22/21. What we're doing today is a quick recap of 10.1 and calculus with parametric curves. Which is 10.2. After this, we will start talking about polar coordinates. Polar coordinates is the last topic in this class. And neither of these things are especially brutal, but there are some concepts that you need to internalize all the way. It's not 100% mechanical. So let's do it. Let me pop open your textbook here. We'll grab just a quick problem or two from 10.1. Kind of treat as a little review. So yeah, if you want to, so from 10.1, there are basically two methods for graphing parametric curves. You can just make a table. Or you can eliminate the parameter. Making a table is what it sounds like. You just make a table where one of the columns are t values and the other column is the ordered pair x comma y. And then you plot those in order as t increases, and make sure to include the little arrows to show orientation. The other option, if you eliminate the parameter, this is where you solve one of the equations for t and then plug that into the other equation. Or maybe use some trig identities, use some algebra trick to get rid of the t's and just have a regular xy equation. And then hopefully that xy equation is one that you know, and you can say that your graph will be a portion of that. Exam 2 grade should be in. Yeah, so if your exam 2 grade is not in yet, then there's something holding it up. Either I haven't been able to get the materials from the testing center. So if your exam 2 grade is not in, take a look at the comments there. Those should all be in. Test 3 date, last day of class. So for you guys, test 3, the last midterm exam, we have class on Fridays, right? So your exam 3 will be next Friday. All right. So let's take a quick example here where we can sketch some parametric curves. How about t squared minus 2t and t plus 1? In the notation we have been x of t equals t squared minus 2t and y of t, what was it, t minus 1, t plus 1. And let's say -2 is less than or equal to t is less than or equal to 3, something like this. Test 3 will cover parametric curves and polar coordinates. All right, so 10.1, 10.2, 10.3, and 10.4, all the stuff we've done. Oh, and of course, power series. So all the stuff that we've done since test 2. So let me clear test 3, which is the last day of class, December 3rd. We'll cover power series, parametric curves, and polar coordinates. The power series material, that's from 11.8, 11.9, and 11.10. And the parametric and polar stuff are 10.1, 10.2, 10.3, and 10.4. Okay. So the first option here is to make a table. So the one column of my table is just t values, and the other column of my table is the ordered pair x comma y I get from that t value. And since I'm told t is running from -2 to 3, I'll just use integers there, -2, -1, 0, 1, 2, and 3. When t is -2, x is 4 minus 2 times -2. That's 4 plus 4 is 8. And y is -2 plus 1, which is -1. When t is equal to -1, x is -1 squared minus 2 times -1. That's 1 plus 2 is 3. And y is -1 plus 1, which is 0. When t is 0, x is 0 and y is 1. When t is 1, x is 1 squared minus 2 times 1 is 1 minus 2 is -2. And y is 1 plus 1, which is 2. When t is equal to 2, we have 4 minus 2, which is 2, comma 2 plus 1 is 3. And when t is equal to 3, we have 9 minus 6, which is +3, and 3 plus 1, which is 4. So my initial point is 8, -1, and then we're going to flow through these points and end at this terminal point, which is 3, 4. So plenty of space over here. Mark this as 8, 4-ish, 2, 1. All right. And then my y values are getting as large as 4, as small as -1. So make this -1, 1, 2, 3, 4. All right, so the point 8, -1 is my initial point. It's over here. And it's the point associated with t equals -2. Then I go through 3, 0, which is right here. Then we go through -2, 2, should be right here. Then we go through +2, 3, should be right here. And then we go through +3, +4, which would be up here. Oh, did I make a mistake in here? Let me double check something. So 2, 3 came from t equals 2, that's 4. Minus 2. So this curve to me started off looking like something like this. I do think I made a little mistake here. I'm so sorry. So 0 gave me 0.1, which I didn't plot, 0, 1. 1 gave me -2, +2, which I did plot 2. 4 minus 2 times 2. Oh yeah, this should be 0. I'm so sorry. This should be 2, 0. Yeah, or sorry, 0, 0, 3. Yeah, I moved up. 0, 3. There we go. Okay. And so what we end up with here is something looking like this. And I call this my terminal point. So I made a little arithmetic sake on the t equals 2 thing, right? When we plug in 2 for t here, we get 4 minus 4, which is 0, not 2. So that point should be 0, 3. And this is my curve. Which modulo my bad art looks like this guy. My initial point is down here. So my orientation or direction of travel, these little arrows, go like this. And if I want to know what curve this is, the other approach we could take here is to eliminate the parameter. The easiest way to eliminate the parameter here, this guy has some t's and t squareds. This guy just has t's. So if I solve this for t and then plug that in here, I will get a regular xy equation. So to eliminate the parameter, I'm going to solve the y equation for t and take that result and plug it into the x equation. Since y is equal to t plus 1, we learn that y minus 1 is equal to t. Therefore, x, which is t squared minus 2t, is y minus 1 squared minus 2 times y minus 1. And this, we can see pretty readily, is going to be a parabola opening sideways. It's a quadratic where x is equal to some combination of y's and y squareds. If we want to see exactly what it is, we could factor a y minus 1 out. And what would be left here is y minus 1 minus 2. So this is y minus 1 times y minus 3. And that makes sense, right? This is a parabola opening sideways whose roots are at 3 and 1, which is what we have. So this would be the regular xy equation. You could say either x equals y minus 1 times y minus 3. Or you can FOIL that out. That's x equals y squared minus 4y plus 3. And I think from the factored form, it's easiest to see that our curve is more or less correct. And again, modulo my bad art. This is a parabola opening to the right, right? It's a left-right thing instead of an up-down thing because the variable it's being squared is y. And the y-intercepts here are 1 and 3 because we have this factored form. Our curve is not the whole parabola because we are given a finite time domain here. We're told t runs from -2 to 3. So my initial point is the point associated with t equals -2. We travel along this curve until we get over here, which is my terminal point associated with the largest t value, t equals 3. Not too bad, right? Okay. There's one topic from technically not in the textbook at 10.1, but I really want to share with you something super duper important in later classes. We talked about parametrizing a curve, right? So if you have a curve, how can you write parametric equations for that curve? The simplest way so find parametric equations for a curve y equals f of x. So if your curve is the graph of a function, which oftentimes it will be, right? Most of the curves that we care about in this class are like that. Just remember that every point along such a curve is of the form x comma f of x. So to do this, we can use x of t equals t and y of t. All that matters is that the y is f of that x. So this would be f of t. This is what I would call the standard parametrization of that curve. You could also use a bunch of other things like x of t equals the natural log of t. And y of t would then be f of that. The truth is, you could use any surjective monotone function for x. Meaning you don't, for your x function, you don't want something that goes back and forth from increasing or decreasing. And you want to make sure that the range is all real numbers. And as long as you pick any function like that for the x, the y is just going to be f of that thing. So other examples, I could use x of t equals t cubed, and then y of t would be f of t cubed. And depending on the domain, you could get away with a non-surjective function for the x guy. It doesn't have to be an onto function. But this is the standard one. And there are, of course, other choices. So let me do an example here really quick, and then we're going to move on from 10.1. Let's find 3 parametrizations for the curve y equals 1 over x, where x, let's say 1 is less than or equal to x is less than or equal to 10. So I'm wanting to parametrize or find parametric equations for not all of 1 over x, just this part from 1 to 10. And let's orient it in this way. And of course, 1 over x has pieces over here as well. This is what I'm looking for. It's just this portion here. the standard parametrization, you just let x be t, and then y would be f of t. So here, would be 1 over t. And here, t would run from 1 to 10 because t is x. We could also do x of t equals, say, t cubed. And y of t then would be 1 over t cubed. And I have to be a little bit careful about the t values that will give me the interval 1 to 10. Here I would want t to run from 1 to the cube root of 10, because that's what's going to make x, which is t cubed, go from 1 to 10. Okay, just to give you a few ideas, other things we could do. I could use for my x function t squared plus 1. Now, t squared plus 1 is not one to one and onto. It's not monotone. So I do need to be a little bit careful to make sure I'm not retracing any portion of this curve more than I want. But I can do that as long as I pick my t values carefully. Y of t here would be 1 over that. And then I just have to ask what t values will make this thing run from 1 to 10. Well, when t is 0, 1 plus t squared would be equal to 1. And when t is 3, t squared plus 1 would be equal to 10. So to get these a's and b's, the t values, you just have to think about getting your domain right, getting the x values that you want. I want this graph from x equals 1 to x equals 10. So if t goes from 0 to 3, t squared plus 1 goes from 0 squared plus 1, which is 1, out to 3 squared plus 1, which is 9 plus 1 is 10. All right, and there's lots and lots and lots of other solutions here. There's infinitely many ways to parametrize any given curve. Just want to familiarize you with the process. So it's something you'll use a lot in Calc 3, physics, elsewhere. Okay, time to talk about calculus. There are 3 major calculus problems that we're going to solve in the setting of parametric curves. So this is section 10.2, which is calculus. We will learn to find tangents, tangent lines, and all the stuff associated with that, right? Mins, maxes, etc. Arc length. I guess there's 4 things: arc length, areas, and surface area with parametric curves. Tangent lines, you know, come from the dy dx derivative. So to solve the tangent problem and all the associated problems, you just need to know how to find dy dx. Yeah. For a parametric curve, x equals x of t and y equals y of t, where both x of t and y of t are differentiable, one can find the normal derivative dy dx, this is the thing that tells you the slope of the tangent line, as the ratio of the time derivatives of x and y. So this would be dy dt divided by dx dt. And of course, there's lots of other notations for this. Call that y prime of t over x prime of t. Just make sure you're careful about saying what variable you're differentiating with respect to. So remember, x and y are both functions of the variable t. We're looking for the derivative of y with respect to x. And to do that, we find the derivative of y with respect to t, and we divide that by the derivative of x with respect to t. The thing that looks like it should work here, where you flip over the second fraction and cancel out the dt's, basically works. But it's not 100% kosher because dt is not a number. There is another notation that's common in physics here. And that is the dot notation. So y dot, dot generally means derivative with respect to time. I'll generally use the Leibniz notation, I think, because it's the most clear, even though it's a little bit clunky. This will allow us to find things like tangent lines. So let's take a look at one or two problems here. Oh yeah, I do need to specify here, as long as dx dt, the thing downstairs is non-zero, of course. Okay. So let's, this one's a little bit gnarly, but that's okay. So t squared and t cubed minus 3t. They want us to do a few things. Show that the curve has two tangent lines at the point 3, 0, and then find the equation of those lines. Don't worry about curvature or second derivative stuff. There are some things in the book here that I'm not going to cover in this section because, frankly, parametric curves aren't the right place to do those things. Yes, you can talk about curvature. Yes, you can talk about d2y dx squared. But if you're going to do that, you might as well do it in the regular setting. There's nothing nicer about doing that with parametric curves. So I'm going to stay focused on the stuff that is appropriate to do in each kind of geometric setting. So what is appropriate to do in the parametric setting are tangents, arc lengths, areas, kind of, not really, but it's not terrible. So I'll show you it's no worse than the regular case, and then surface area. Okay. Just for gits and shiggles, before we dive in here, let me go ahead and take a look at the graph of this thing. So I think it will help us to understand what they're saying. t squared and t cubed minus 3t. And let me open this up from like negative. There we go. All right, here is our parametric curve. The x's are all t squared, the y's are t cubed minus 3t, and undeniably, this curve at the point 3, 0 has two tangents, right? You can think of this as the motion of a particle. So I'm just going to put in a second thing here so you can watch this thing move. Oh, it's not showing up. Oh no, it's very ordered pairs. All right. We can watch this thing move. Come on. There it is. Oh, I wrote the wrong thing. S cubed. There it is. Okay. So here's that particle moving around. He comes in from below, goes through the point 3, 0, spins around here, and then exits going up. So there's one tangent line that comes from this path, right, where he's going out, and there's one tangent line that comes from here. That point 3, 0, right there. And if I wanted to take a guess at what that tangent line is, well, I know it's going to be something like some constant times x minus 3. And I can take a look at the possible tangent lines there. So something like this, that kind of looks like one of my tangent lines. And something like this looks like one of my tangent lines. Thereabouts, right? But I want to find the equation of those two tangent lines. That's my goal. So how would we verify that there are two tangents without Desmos? Well, I'd have to show, remember what the logic that we're using here, this particle comes through here twice, right? If I track this particle's motion, he comes through here once around the time t equals negative 1-ish, and then he comes through here again around the time t equals positive 1-ish. So I want to verify that this curve passes through this point twice. So for part A.
Is there any way you can find out it passes through that point twice without like plugging it into Desmo?
Yeah, that's what we're going to do here. So for part A, if we want to do this without relying on graphing utilities, we show that the curve passes through 3, 0 twice. What that would mean is that there are two different times. There are two different t values such that these equations go through this ordered pair, i.e., there are two solutions to x of t comma y of t equals 3, 0. That's what we're trying to show. All right, so the points on the curve are all x of t comma y of t. And if I want to show that this curve goes through 3, 0 twice, that means there should be two t values. The solutions are t values. So this means x of t would be equal to 3 and y of t would be equal to 0. X of t is t squared, so t squared is equal to 3. And y of t is t cubed minus 3t is equal to 0. This gives me t equals plus and minus the square root of 3. Boom, there's your two solutions. And if you just want to check, factor in a t here, you get t squared minus 3 equals 0. So here you have t equals 0 and t equals plus minus square root of 3. And if you want to take this work and interpret it, this means that the x coordinate of that point will be equal to 3 twice. Once when t is the negative square root of 3 and once when t is the positive square root of 3. This means that the y coordinate of that point will be equal to 0 3 times. Once when t is the negative square root of 3, once when t is 0, and then once again when t is the positive square root of 3. So this is part A. So all of this work collectively here shows the curve passes through three comma 0 twice. Once when t is equal to the negative square root of 3, and again when t is equal to the positive square root of 3. Why am I not taking the t equals 0? I got plus minus root 3 from both of these, but from the y equation, I also got t equals 0. Why is this not one of the t values that sends me through the point 3 comma 0? Yeah, it came from the y and just the y. So y is equal to 0 when t is 0, but x of t is not equal to 3 there. In other words, when t is 0, we're at the point 0 comma 0 comma 0, not 3 comma 0. So he's not a part of this. We don't go through that point 3 times, we just go through that point twice. And again, that's what we saw with the picture, right? So here's that first one. That's when t is the negative square root of 3. Here's the t equals 0 point. That's not 3 comma 0, that's 0 comma 0. And then here's the next one. That's when t is equal to the positive square root of 3. All right. So we run through that point twice. Now I want to find those two tangent lines. That's what's next. Looks like I got one here. And here, something like this. So how do I find those? Well,
Professor, could you explain again why the t equals 0? It's irrelevant.
so when t is equal to 0, this curve is not at the point 3 comma 0. When t is equal to 0, we're at the point 0 comma 0. Let me see if I can still, there we go. So here we are passing through that point the first time. That's when t is the negative square root of 3. Here we are passing through that point the second time. That's when t is positive square root of 3. When t is equal to 0, we're not at the point 3 comma 0. Our y coordinate is equal to 0, but our x coordinate is not equal to 3. So the t values where our curve passes through 3 comma 0 will be the t values where x is equal to 3 and y is equal to 0. It's true that y is equal to 0 at both of those square roots of 3 and also t equals 0, but it's not true that x of t is equal to 3 there, right? If you plug in 0 to the x equation, you get 0, not 3. So in other words, our curve passes through 3 comma 0 for any t value that satisfies both of these equations at the same time. We need the y coordinate to be 0. That's true because That's the y coordinate of this point. We also need the x coordinate to be 3 in order to be at this point, because the x coordinate of this point is 3. So when t is equal to 0, we're at the origin, not 3, 0. In mechanical terms, what you would do is you'd take the intersection of these solution sets. Right? So I get plus and minus root 3 here. I get plus minus root 3 and 0 here. I would take just the stuff that is common to both of those, which is plus minus root 3, not t equals 0. Okay.
Thank you.
Of course. For part B, I want to find I need to find the equation of both tangent lines at the point 3, 0. And we need to remember our curve goes through 3, 0 when t is equal to the negative square root of 3 and when t is equal to the positive square root of 3. The thing about this is when you take your derivative here, it's going to have t's in it, not x's. So when you plug into your derivative to find the slope of the tangent line, you'll be plugging in t values. And those t values are going to be these t values, the t values where we go through that point. The slope of the tangent line, just like good old Calc 1, comes from dy dx, which is dy dt divided by dx dt. The y equation here was t cubed minus 3t. Oh, I'll just write it over here. Y is t cubed minus 3t, and x is t squared. So dy dt is the derivative of this with respect to t. That's 3t squared minus 3. And dx dt is the derivative of this, which is 2t. So the slope of the tangent line when t is equal to the negative square root of 3 is my derivative evaluated at t equals negative square root of 3, which is 3 times negative root 3 squared minus 3 divided by 2 times 3. If you square the negative square root of 3, you get positive 3. 3 times 3 is 9, minus 3 is 6, divided by 2 times 3 is 6. Oh, really? So is that slope just 1? Looks like that slope is just 1. Did we do this right? Root 3 squared is 3. 3 times 3 is 9. 9 minus 3 is 6. Yeah. Okay. And when t is equal to the positive square root of 3, the slope of the tangent line is dy dx evaluated at t equals positive. Oh, no. I'm sorry. This is a square root of 3. I'm so sorry. I knew something looked funky there. This should be 2 times negative square root of 3, right? Yeah, so sorry. So that numerator is 6. That denominator is negative 2 root 3. And then you can cancel 6 and the 2. You get negative 3 over the square root of 3, which is just negative square root of 3. Okay. Yeah, I was thinking that looked awfully weird. This is a 2t downstairs, and I'm plugging in negative square root of 3 for t. The other fellow, that's 3 times the positive square root of 3 squared minus 3 divided by 2 times the positive square root of 3. This is still 3. 3 times 3 is still 9. 9 minus 3 is still 6. And downstairs we just have positive 2 root 3, which is 3 over root 3, which is just root 3. So what are my tangent lines? The tangent line from t equals negative root 3 is, remember your point slope formula, it's y minus y0 equals m times x minus x0. We're going through the point 3 comma 0, so y0 is 0, so this is just y equals slope negative root 3 times x minus 3. That's your first tangent line. And the other one, the tangent line from t equals positive root 3 is y minus y0 equals m times x minus x0. Again, just that regular point slope thing. Our point is still 3 comma 0. So this is still just y equals, but my slope is the square root of 3. So these are my two tangent lines that pass through tangent lines of this curve at the point 3 comma 0. If we look back at Desmos, I can enter these explicitly. There's the first. There's the second. And that's the whole picture. The tangent line over here at x equals 0 would be a vertical tangent line. His slope would be undefined. But over here, we're able to calculate those slopes with no problem. Just using the recipe that dy dx is dy dt divided by dx dt. Questions on this one? Okay. So if I give you some parametric curve and I say find the slope of the tangent, or I say find me the tangent at some point, then all I'm doing is asking for the derivative dy dx, and then you plug the t values in to get your slope there. There are some other problems related to tangents. I could ask you, like, where are the vertical or horizontal tangents for a particular curve? Let me see. Yeah. Like we could ask, where does this guy have vertical or horizontal tangents? Let me go ahead and do number 17 for you. Write this down. At what points x comma y is the tangent horizontal? I'll say or vertical. And then we'll use x of t equals t cubed minus 3t, and y of t equals t squared minus 3. Well, you know that the slope of the tangent line comes from the derivative dy dx. And a horizontal, I'll write this like this, HTL, horizontal tangent lines, mean that the slope of the tangent line, which is dy over dx, just dy over dx is equal to 0. And vertical tangent lines mean that the slope of the tangent, which is dy dx, is going to 1 of plus or minus infinity. So I'll just recall this from Calc 1. A horizontal tangent line is a place where the regular dy dx derivative is 0. The slope of the tangent line is 0. A horizontal line is a line with slope 0. A vertical tangent line is a place where the slope of the tangent, dy dx, is blowing up to infinity. Right? A vertical line has infinite or undefined slope, if you like. So what we want to do is find the t values that make dy dx 0 or make dy dx blow up to infinity, and then plug those t values back into the original equations to find the ordered pair x comma y, the point on the curve. Let's do it. So if I'm looking for horizontal tangent lines, I'm going to set 0 equal to dy dx. And dy dx is dy dt divided by dx dt. Dy dt is 2t, and dx dt is 3t squared minus 3. So what you're looking for here are places where the top is 0 and the bottom is not 0. That will give you a horizontal tangent. So this apparatus is going to be 0 if and only if the top is 0, which means t is 0. You want to check to make sure that that value does not also make the bottom 0. If the bottom was also 0 there, then you would investigate using a limit, using L'Hopital's rule or some other algebra trick. But here there is none of that. So our horizontal tangent lines only occur when t is equal to 0, and the ordered pair there is going to be the point on the curve, which is x of 0 comma y of 0. If I plug 0 into the x equation, I get 0. If I plug 0 into the y equation, I get -3. So that is the answer for my horizontal tangent. So one such point, and it is the ordered pair 0 comma -3. Vertical tangent line. These would be places where dy dx is blowing up to plus or minus infinity. And dy dx, we calculated already, is 2t over 3t squared minus 3. If you factor the bottom, that's 3 times t squared minus 1. So this is 2t over 3 times t minus 1 times t plus 1. So dy dx will blow up to plus or minus infinity as t gets closer to plus or minus 1. Right, those t values which make the bottom 0. So there's two of them, right? One is coming from t equals -1, the other one is coming from t equals +1. But you need to be careful about what the question is asking for. It's asking for ordered pairs. So you need to find the point on the curve where t is -1. You need to find the point on the curve where t is equal to +1. One of those, x of -1, comma, y of -1. If you plug -1 into the x equation, you get -1 cubed minus, it's a minus, not a times, minus 3 times -1. That's -1 plus 3 is +2. And if you plug -1 into the y equation, you get -1 squared minus 3, which is 1 minus 3 is -2. The other ordered pair is coming from x of 1, comma, y of 1. If you plug 1 in here, you get 1 minus 3, which is -2. If you plug 1 in here, you get 1 minus 3, which is also -2. So these are your ordered pairs. You have horizontal tangent line at 0, -3, and you have two vertical tangents, one at 2, -2, the other at -2, -2. We look at the graph. That was t cubed minus 3t, comma, t squared minus 3. Here it is. So here's that curve. And I said that there should be horizontal tangent lines at only one point, which was 0, -3. Here we go. And yeah, I think we would all agree that the tangent to this curve right here is horizontal. That's just the line y equals -3. Vertical tangent lines at two places. So -2, 2. Oh, sorry, 2, -2. 2, -2, that's one of my vertical tangent lines. And at -2, -2, that's the other vertical tangent. And the equations of those vertical tangent lines would be x equals -2. There it is in green. And the other one would be the equation x equals +2. There it is. So yep, this curve has one horizontal tangent and two vertical tangents. One there, one there. It's not too bad. It's the same stuff you did in Calc 1. The only thing you need to remember for any of the tangent-related stuff is how to find dy dx. dy dx is dy dt divided by dx dt. That's literally the only new thing. Everything else, Calc 1 stuff. Last call for questions on how we did this. Okay. Next, I want to talk about areas and arc lengths. Areas are kind of boring. This regular area, so area bounded All right, this is the other classic calculus problem, finding the area bounded by a curve. Just like we can do all the tangent stuff, we can do all the area stuff. Recall? I know everybody remembers this. The area bounded by the curve y equals f of x from x equals a to x equals b is just the integral from a to b of f of x dx. There's a reason we always write y equals f of x when you're looking at a graph. It's because the y values on that curve are f of those x values. That's how the curve is defined, right? So if I'm looking for this area, you just integrate that function, right? Well, we did this a lot at the beginning of the semester. And we saw this in Calc 1 as well. Remember that the point here, x comma y, is the point x comma f of x. So in other words, f of x is y. If you want to find the area bounded by a parametric curve, so similarly, the area bounded by a parametric curve x equals x of t, y equals y of t can be calculated as the integral, say from t equals, what do I want to call it t0 to t equals t1 of y dx. Remember, everything here, both x and y, are now functions of t. So y, this is really y of t, and dx is going to be, let's say this is integral from t0 to t1 of y of t times x prime of t dt. Because if x is x of t, this means that dx, just like you're calculating differentials for u sub, is x prime of t dt. In fact, this is u sub. It's a cleverly disguised version of u sub. I won't go into those details. But I'll tell you, this is what you integrate. It's a little height times a little width. Right? That's it. Remember, x primed, or dx dt, tells you how fast you're moving left or right along that curve. So x primed of t dt is a tiny little width. It's a little horizontal width. And y of t is your height. You can set this up with Riemann sums, but I don't think anybody wants to do that. Here, T0 and T1 are the T values that give you the points you're trying to integrate between. So if I have some parametric curve, maybe it does some wonky shit over here, it does some wonky shit over here. But I'm interested in finding the area bounded between these 2 points. Call it A, and call it B. So here's the graph of my parametric curve. I can't always talk about area bounded by the curve and the x-axis like over here. That would be a real problem. But in here I can. So anywhere it makes sense to do this, anywhere my parametric curve does in a reasonable way bound area with the x-axis, I can calculate that area. Saying, okay, this is the point associated with T naught, T equals T naught, and this is the point associated with T1. And if you want to, you can think of a little Riemann rectangle in here. The height would just be y of t, and the width would be x primed of t dt or dx. Nothing too bad, but you do need to remember this. We really are just integrating y dx, which since dx is x primed of t dt, is the integral of y of t times x primed of t dt. And your bounds are going to be t values, not x values. The t values you find by figuring out where x is equal to the x value you want to work with and where y is equal to the y value, or where x is equal to the second x value you want to work with. We can crunch out a quick example. The ellipse is the problem I put in your homework. Let's see, what would be a fun example? Area enclosed by the x-axis and the curve. Yeah, okay. Let's look at t cubed plus 1, 2t minus t squared. And so 2t minus t squared. Okay. And we can swap this t cubed s cubed. 2s minus x cubed. And everything else can go away. All right. So I want us to find the area bounded by this curve and the x-axis. And the only region here where we're bounding some area, if I gave you this problem, for example, on a test, I would have to give you the graph. That means we're going from x equals 1 to x equals 9. Let me write this down. I want to find the area. Here's how I would put it if I put this on a test. X2 plus t cubed plus 1. Y2 squared. From x equals 1 to x equals 9. Oh, so a few little challenges here. First, even if you have the graph, you have x values here, not t values. So I need to find the t values that correspond to these x values. Second, this is not a curve y equals f of x. So I have to set up the integral as a parametric curves integral. So first we find the bounds. X is equal to 1 means t cubed plus 1 is equal to 1, which means t cubed is equal to 0, so t is 0. The first point is the point associated with t equals 0. Also, x is equal to 9 would mean that t cubed plus 1 is equal to 9. T cubed is equal to 8. So t would be the cube root of 8, which is 2. So I'm integrating from 0 to 2. The area is the integral from 0 to t1 of y of t times x prime of t dt is the integral from 0 to 2. Y of t is 2t minus t squared times x prime of t dt, which is 3t squared dt. And that's it. That's your integral. We can distribute 2t times 3t squared is 6t cubed. T squared times 3t squared is minus 3t to the 4. And we can take our antiderivative. You could factor out a 3 if you wanted. I won't even bother. This is 6/4 t to the 4 minus 3/5 t to the 5, evaluated from 0 to 2. When we plug in 0, we don't get anything here. These are both 0, so everything comes when we plug in 2. This is 6/4 times 2 to the 4 minus 3/5 times 2 to the 5. 4 is 2 squared, so this is 6 times 2 squared is 6 times 4 is 24, minus 2 to the 5 is 32. Not much we can do with that, so 32 times 3 would be 96/5. And I would be fine with you leaving it like this. If you want, you can write 24 as a ratio over 5. What is that? 120. So 120 minus 96 is 24 fifths. So I'll write it out. This was 120 over 5 minus 96 over 5, which was, double check myself here, 24 fifths, yeah. All right, that's it. That is this area. So areas in parametric coordinates, not for parametric curves, not super exciting. Namely, because anytime you could do this, right? Anytime you have a parametric curve where there is a meaningful way to talk about the area enclosed, you could have just eliminated the parameter and done it the old-fashioned way. I could solve this for t. T would be the cube root of x minus 1. And then I plug that in here. And then I could just integrate this from 1 to 9 after plugging in t cubed minus 1 for x, or x cubed minus 1 for t. The integrals are never easier or harder if you set it up the old-fashioned way or you set it up in the parametric form. They're always the same integral. But what is fun in this system is arc length. Now I realize we are at time, so let me just give you the recipe for arc length, and next time we will talk about it in detail. Arc length is what it sounds like. I have some parametric curve, and I want to find the length. What I'm asking is, if you think of this as a rope, and I stretched it out, I shouldn't say stretch, but if I straightened out this curve, how long would it be? Kind of the way you normally get there. Y-axis is your x-axis. Is by approximating with straight line segments. And then what you see is each one of those little straight line segments has a length that can be calculated using the Pythagorean theorem. So if this is the point associated with t equals a, and this is the point associated with t equals b, then the arc length, and I believe your book uses the symbol L for this, which is unfortunate because pretty much everywhere else uses S, but they don't use S for surface area, would be the integral from t equals a to t equals b of a pretty intimidating looking thing. It's dx dt squared plus dy dt squared dt. And that's because each one of these little length segments is coming from the Pythagorean theorem. And if I take the length from here to here, and I approximate it by a straight portion, this is like, I should say delta x, and this is like delta y. So this little length, which would be delta L, would satisfy delta L squared equals delta x squared plus delta y squared, which means that your delta L is the square root of delta x squared plus delta y squared. And then to get from there to this integral, you technically would build up a Riemann sum out of these, multiply through by delta t over delta t, shove one of them inside, that gives you the delta x over delta t squared plus delta y over delta t squared, and leaves you a delta t outside to form dt in your limit. I'll go through the full derivation of the arc length formula in class next time. I'll do it somewhat quickly. This is the gist. These integrals tend to be kind of challenging, and you have several of them in your homework. The good news is that you don't need to understand the derivation to understand how to use this. So if you want to, you can get started on those problems today, and that homework set is already posted for you. I definitely want you guys to work on the tangent stuff, all of the tangent problems from the parametric curves before class on Wednesday. And then on Wednesday, we can talk a little bit more about arc length of parametric curves. I'll solve a handful of examples using this recipe. And then we're going to talk about surface areas of parametric curves. And that will be the end of our discussion of parametric curves. After that, in our very last bit of class, we're going to talk about polar coordinates. This is where I'm going to leave it for today. I will see you guys on Wednesday.